Okay, let's go. Session number 8 in this chapter is about the energy stored in a magnetic field. We accept this formula. This one will be proved in a chapter of planar waves. Okay, so like the energy stored in electric field, in a magnetic field we have an energy. We have an energy like this, and this one, as you can see here, is a volume integration of the dot product between the magnetic flux density and MFI. We can do the unique example about this. The unique example about this one. So we reconsider this exercise. A long time ago, we found the MFI created by DC current flowing through a conductor, an infinitely long conductor like this. Okay, and last time we found that this is the magnetic, the MFI inside this conductor. So we can compute the energy stored by applying this formula. Okay, in this formula, we have to find the energy stored in a unit length, meaning that we can take the length of this one from 0 to 1 meter, for example. So this one is the expansion of the very small volume, and we in this formula, because the length of the volume here is fixed, and nothing changes alongside the axis of this cylinder, so we take the integration with respect to the radius only, and here we are. Please notice that this energy here is independent of the dimension of this cylinder, this conductor. Okay, you don't see any radius in this formula. Now we need a story about the exterior volume. In the exterior of this conductor, we found this, and if we apply this one to the energy stored inside the magnetic field, we will come to this one. If you, how can I say, if you remember that this one is an infinitely long cylinder, so you can think that this result here is reasonable, because this cylinder here is very long, so the energy that it created is extremely large. The last session of this chapter is about inductance and mutual inductance. We knew about two previous electrical parameters in a circuit. They are resistor and capacitor. I mean, they are resistance and capacitance. Now will be the last one, inductance. So this is a magnetic flux. We knew this, okay? And this one is Ampere's law. If you compare this one and this one, you can see that the magnetic flux is proportional to the current. And so we can define the inductance of a coil like this. According to this, the inductance is the ratio of the magnetic flux to the current. If the coil has only one turn, then here it is. If the coil has n turns, then we have to multiply 5 here to n, and then we have this definition. Okay, based on this, we're trying to do several examples. Let's consider this coil. Everything was given here: the magnetic flux, the currents, the dimension, except of course the inductance. So if you look at this, you can see that if you want to find the inductance, you have to know the magnetic flux, okay? because we are given n and I. Firstly, applying the right hand, you can see that this is the direction. If this one is the direction of the current, then this one is the direction of the magnetic flux. And based on the definition of magnetic flux, we have this formula. Okay. A long time ago, we found that the magnetic flux inside this system is approximately constant. And so we can figure out the output of this integration like this. Okay. So we find the magnetic flux, but actually we didn't find this because so far we don't know yet the MFI-H here, so we have to find this. To find this one, we can apply once again Ampere's law. For example, give me 1 minute to change the color of the pen. For example, I draw like a closed trajectory like this, okay, and I applied Ampere's law to this rectangular trajectory. We knew that inside the coil, the magnetic field is constant, and in the exterior of the coil, from here alongside this to here, there is no MFI. So the left side here will be H multiplied to the length of the section of the trajectory inside the coil, and that length is D. See here. So the left side here is H times D. From here we can find H, and substituting this one into the magnetic flux here, we can find the magnetic flux. And finally, if you put this one into the numerator of this definition, you can find here the inductance. The inductance here is proportional to the relative permeability of the environment, to the square of the number of turns, and to the square of the cross-sectional area of the coil. And this inductance is inversely proportional to the length of the coil. There you are. So we can see that if you have to find the inductance of a system, of a given system, you can rely on the definition. Okay, and to come to the final answer, you have to find the magnetic flux. And if we don't know the MF5, then we have to find this to come to the final answer. Second and the last example of finding inductance. We had to find the inductance of this coaxial cable. In previous chapter, we found that this is a total magnetic flux flowing around the inner cylinder. So of course, we knew the magnetic flux, so finding inductance is very simple. Okay, and it's a phi over I, and there you are. The inductance here, of course, depends on the length of the cable. So if you want to find the inductance for every meter length of the coaxial cable here, you can change D here into number 1, and there you are. There are 2 remaining examples, and of course we don't have time much, so I leave them for you to do by yourself. Okay. I now come to the last one of this chapter. It is about the mutual inductance. This is the definition of the mutual inductance. We have this kind of parameter if we have two coils being very close to each other like this. So in this formula, phi 1, 2 is a common section, how can I say, common path of the magnetic flux between the two coils. And I1 is the current of the first coil, and N2 is the number of turns, of the second coil. If you look at this, and if you take a look back at the definition of of inductance, you can see that they are very similar. Okay, there is the ratio of the magnetic flux to the current, like this. The ratio of the magnetic flux to the current. So once again, M here must have the same unit like L. It is Henry. I think everybody knows that this one is Henry, right? So once again, finding M is to find the magnetic flux. I will illustrate that idea by doing the unique example for this session, this one. We have two circular circuits like this. They are parallel to each other, and the centers are on the same axis like this. The common axis here is perpendicular to both frames. The radii of two frames are A and B respectively. Now we have to find the mutual inductance between the two coils like this, provided B is much smaller than A. From the very beginning of steady magnetic flux session, we knew that this one is the MF5 at any point alongside the axis, the symmetric axis. Okay. And because B is much smaller than A, so firstly, there is a magnetic flux like this, okay, flowing like this, for example. So, because B is very, very small compared to A, so we can think that the magnetic flux flowing the MF5 going through this smaller circle is uniform. Okay. Then, because the magnetic flux flowing through this one is uniform, then the total magnetic flux will be the density multiplied to the area of a smaller circle. The density will be H multiplied to the permeability of the environment, which is mu0. And the area of a smaller cylinder is pi b squared. And finally, we can find the how can I say the linking inductance between the two coils like this, and there you are. Finding mutual inductance is little difficult than finding the inductance, but they have the very common thing. It is that we have finally to find the magnetic flux going through something. Okay. All right, so that is the end of this chapter. Before finishing this, I will once again showing a summary about this chapter. In this chapter, the first session is about the interactive force of the magnetic flux. So let me remind you that this one is a force that a magnetic field acts on a circuit L carrying a DC current I. Okay. So this is the interactive force between a magnetic field and the circuit. So this one is a translational force. If we care about the rotational force, I mean, then we have to change the force here into the torque, and this is a definition of torque. Okay. This is the first half of this section, this chapter. The second half of this chapter is about the inductance. This is a definition of the inductance, and we also defined the mutual inductance M. Đây quá. So do you have any question about this? Okay, then this is the end of this chapter. We come to the final one. Give me 1 minute. Okay, the last chapter of our course, time varying fields and Maxwell equations. We are entering the third part of this course. It is about time varying fields. Okay, so in previous sessions, previous chapters, we established the relationship, the fundamental relationships between of electrostatic fields and static magnetic fields. In this chapter, we study the time varying fields. Some relationships remain the same. Some other changes. Some others change a little. So in this very important and a little difficult compared to previous chapters, we talk about 5 things. The first thing is about Ampere's law. Faraday's law. In 1820, Christian Ørsted found that a current can move the neuron of a compass. From that experiment, Faraday had an idea that if a current can produce a magnetic field, then in the reverse direction, maybe a magnetic field can produce a current. This is a reconstructed figure of the experimental system that Faraday worked on. And this one is a photo of the ring coil used in that system, in that experiment. So, after 10 years of studying, researching, Faraday found that if there is a time-varying magnetic flux flowing through a frame, then that system will produce an electromotive force, EMF. EMF here stands for electromotive. I will type that one in the chat box. Give me 1 minute. Where is that? Here it is. EMF is electromotive force. You should know this. Hiểu á? This electromotive force is actually a potential, and the potential here will exist if we have one of these three following conditions. The first one is that if the magnetic flowing through the coil is changing in time, if the magnetic flux flowing through the coil changes in time, or if that magnetic flux does not change, but there is a relative a relative motion between that magnetic flux and the coil. And the last one is that if we have both, then of course there is an EMF. What about this sign? I think you knew this. According to Lenz's law, this is minus. This law says that, give me 1 minute, it says that the EMF here produces a current. That current in turn produces another magnetic field, and that magnetic field is opposite to the previous magnetic fields that produce the previous current. Okay. So let's take a look at this. On the one hand, like I told you, this one is a potential. So on the one hand, the potential can be found from this, can be computed from this. On the other hand, because the EMF is the potential, so it must follow the definition of a potential, which is this. Okay, so we try to figure out something from this. The numerator here can be found from this, the area integration of B dot ds. Combining all of this, we come to this one. Okay. I change E here into d phi over dt. I mean that I change phi here into the the area integration of B dot ds. And because we are talking about time varying field, so in the different case, B here must be a time function, a time varying function. Okay. And then because this one is the integration with respect to position, and this one is the derivative with respect to time. So d over dt is a constant. Then we can put this one under the integration sign, and here you are. Of course, we have to change D here into delta because B now here will be a multivariable function. It depends on both time and position. So we have to change D here into delta. Okay. All right. So this one is the right side. Now we care about the left side. According to Stokes' theorem, the left side here, which is a line integral, can be changed into a surface integration by taking the rotation of the field under the integration. Okay, in short, we have this. So the right side here must be equal to the right side here. Both are surface integration. So the two expressions under the two integrations must be the same. We can remove ds from both sides, and finally we come to Maxwell's equation for time varying function. So this formula here says that the rotation of EF5 is equal to the rate of change of the magnetic density with respect to time. So this is the first time we see the how can I say, a combination of four very important quantities in this course. It is the EF5, the MF5, the time, and the space. Please remember that the rotation here is a difference with respect to space. Okay, four quantities: EF5, MF5, time, and space. Okay, we have this. If we are now in a steady magnetic field, so we can suppose that this one is 0, and from this assumption we come once again to two very familiar results. First one is the energy conservation law. Remember this. And the second one is Maxwell's equation for steady magnet for invariant fields. Okay, we consider this very simple case. We have a U-shaped conductor, and we have a free moving we have another free moving conductor. This blue conductor here can move freely on the U-shaped conductor. The whole system is in a rectangular coordinate system like this, and it is in a uniform magnetic field B. The field here is perpendicular to the surface of the U-shaped conductor. Let's suppose that the blue conductor here is moving alongside the y-axis with the speed of v. Now we try to apply Ampere's law to this case. This magnetic field flowing through the this rectangle, okay? And because B here is uniform, so this one will be B times the area of this rectangle. The area of this rectangle will be D times Y. Let's say that this length is Y, okay? There what? The induced voltage can be found from this formula. We find the derivative, the rate of change in time of phi. From here, we have this. So you can see that if this bar is moving, then there is an EMF, okay? Because in that case, V here is non-zero, then the result here will be non-zero. If there is no movement, meaning that if V here is 0, so obviously this induced voltage will be 0. So this is the first result. We try to find another one from this very interesting experiment. We knew from the previous chapter that this is the interactive force between the fins and chassis. Because there is an induced voltage, so there must be a current flowing through the rectangular frame like this. And we know that the current is a collection of moving chassis. So there are moving chassis flowing alongside this conductor. Okay, and because they are moving inside the fins, so there is an interactive force between the moving chassis with the speed of v and the fins. If I divide both sides by q, then we have this. And remember this, from the very beginning chapter of this course, we knew that the ratio of the force to the charge is the EF phi. Okay, then the left side here is the EF phi. But this one is not the normal EF phi. This one is not the EF phi of an electrostatic field. This one is EF phi, the EF phi of a time varying field. So to distinguish between them, we add an index to this EF phi m. M here is motional. Okay, M here stands for motional, meaning that we are talking about the induced EF phi created by something moving. In this case, it is the chassis. And then we return to the induced voltage. It is a voltage, so it can be defined by this formula. On the one hand, you know that EM is a V cross B. So if we apply to this, we have this one. V cross B will be V times B, because the angle between B and V here is 90 degrees, and sine of 90 degrees is 1. And for the second time, we come to the very same result that we found using the direct definition of Faraday's law. Right? So, to compute EMF here, there are two ways. The first one is that we can rely on E dot dl, the line integral of E dot dl, or we can rely on the summation of emotional fields, electric fields, I mean, like this. So this one here is a general case of the induced voltage. This formula explains very well the three conditions to have a non-zero EMF. If we have a time varying field, meaning that if delta B over delta D is non-zero, so there is an EMF. If B is a constant field, but B is a relative moving to the frame, meaning that if V here is non-zero, so EMF is a non-zero. That is the second condition. And of course, if we have both, if we have a time varying field and we have a moving field, moving frame, then of course we have an EMF. Okay, a simple question. Let's consider this case. I have a frame here, I have a switch here, and the whole system is inside a uniform field. I close and I open this switch. Okay, I open it, I close it, I open it, I close it. So tell me, is there any EMF in this case? Can you answer my question? Okay, I repeat once again. I have a frame like this. Of course, this one is conductive frame, and it is inside a uniform field B. I open the switch, I close the switch, I open it, I close it, open it, close it many times. So tell me, is there any EMF in this case? Yes or no? we can consider this formula. Is there a time varying field in this case? No, because we are supposing that the field is uniform, so there is no delta B over delta T. Is there a relative motion between the frame and the field? No, there is no relative motion. So V here is 0, and therefore we can come to the conclusion saying that in this case there is no EMF. Okay. All right. So do you have any question about this very important formula? This one is the backbone of this chapter. Any question for this?
Excuse me, teacher.
Yeah.
Can you explain a little bit about the integral, like integral S and closed integral? What is the difference? And can you explain both the integral areas?
Okay, for the switch here,
No.
I open the switch. Okay.
No, I'm asking about the equation. In this equation, first we have minus integral S ds. For this integral, can you please explain this area?
Are you talking about this?
Yeah. Can you
please
explain the uppercase and lowercase of this integral? Did you get my idea?
This integration is about the EMF produced by a time varying field. Okay. If the time,
it means like the cross area. Cross area.
What do you mean cross? Yeah. S here is the cross area of this one. Okay. S here, if you take the integration, we have to take the integration over the whole area of the frame here.
All area crossed by the.
That's right. The whole area crossed by the field.
Okay. So then the other closed integral.
In this one.
Yeah, in this one.
And here is the edges of this rectangular frame. Okay, it is the total perimeter of the frame. And here is the total perimeter of the frame.
It must be a closed area, but we consider only L.
Yeah, because if the if N here is unclosed, then there is no current, because the current can flow only alongside a closed circuit.
Closed. Okay. Thank you, teacher.
Never mind. Any other question? All right, so we do the first very simple example. We have a turn, and this one is in the air, meaning that we have to use mu0, and the whole system is in a uniform magnetic field. The field here is perpendicular to the surface of the turn of the frame. The total area of the frame is 10 meters squared. We are given the rate of change of B like this, and we have to find the induced voltage. This one is the original definition, original formula of Faraday's law. EMF is proportional to the rate of change of the magnetic flux with respect to time. Okay. On the one hand, because this one is a uniform field, so the magnetic flux will be the the density multiplied to the area. Okay. And from here we can infer this, and that's it. The rate of change dB over dt here is 5 Tesla per second. The total area is 10, and There what? We can remove these minus signs because the sign here just to say that this induced voltage is against the original field. Are you okay? Of course, this example I think is too simple. We now work on a little more complicated examples. Okay, this one. We have a rectangular frame. Sorry, we have a rectangular frame and the current. The frame and the current here are on the same surface, which is your screen. The frame here is moving far away with the speed of v. Because there is a relative motion between the frame and the fins, so there must be an induced voltage, I mean an EMF. And now we have to find that EMF. A long time ago, I think 2 weeks ago, right? We found this. This is a total magnetic flux flowing through this rectangular frame. And now if you want to find the induced voltage, all you have to do is to apply Faraday's law. You take the derivative of this one with respect to time, and that's it. Let's take a look at this. Obviously, this EMF will exist if and only if there is a relative motion. Because if there is no motion, then V here will be 0, and obviously there will be no EMF. The induced voltage, as you can see here, is proportional to the current, and inversely proportional to the time. When time increases, because the numerator here is the constant, and when time passes, the denominator here is getting bigger and bigger and bigger, and then finally the whole ratio here will come to 0. Okay, so you can see that when time passes, EMF here will no longer exist. It is very understandable because when time passes, this frame will be very, very far away from the current, and at that very far away position, there is no field, so there is no induced voltage. Okay. So so far at the moment, finding induced voltage is not very hard. All we have to do is to find the magnetic flux. And how to find magnetic flux? That problem was solved in the previous chapter. Okay. All right. Let's have a break. 10 minutes. Okay, sorry, I missed a little. Sorry, I'm late a little. So let's return to this. If you want to find the induced voltage, all you have to do is to find magnetic flux. Okay, I did my job, so now will be your turn. Remember the mid-class exercise that I gave you a long time ago? Last time, I asked you to change the rectangular frame here into an equilateral triangular form, moving with the speed v. Okay, now I'll give you 5 minutes to find the induced voltage on this triangular frame. Okay, you can take the result that you found a long time ago and to find the corresponding EMF. Okay. All right, go ahead. 5 minutes. Are you done? Keep moving. Once again, we return to this example. In this example, we have a rotating frame in a uniform field. The frame here is spinning about its axis with the speed of omega, angular speed of omega. Once again, a long time ago, we found that this is a magnetic flux flowing through this rectangular frame. Okay, and to find the EMF, all you have to do is to take the derivative of this one with respect to time. And that is a very simple work. So in this case, you can see that the magnetic flux and the induced voltage here are two signs having the same angular frequency omega, and the phase difference between them is 90 degrees, like this. This is the first method to compute the induced voltage, EMF. I will show you the second method later. Now, we do this first question example. We have a rotating bar, okay, solid bar about its end here with an angular speed of omega. This one is rotating, is spinning in a uniform field. The field here is parallel to the z-axis. We have to find once again EMF induced between the two ends of this bar. The problem here is that because we don't have a closed trajectory, so we cannot find the magnetic flux, the magnetic flux, because there is no frame, so there is no magnetic flux. Then how can we compute this? This is a solution. You know, there are two ways to compute this, to compute EMF. The first one is the first term. The second method is to compute the second term. If we don't have any frame, so we can rely on the second term by computing the EMF using the emotional EMF, okay, 3 cross B. If there are charges inside this bar, they will spinning about the z-axis with the speed of v, and that speed can be found by this one. We multiply the radius to the angular speed, and to have the translational, let's say that the tangential speed. Okay. Let's consider a very small section of this strip. The position of this one is rho, the length of this one is d rho. So if d rho is very small, so this one is the common speed of charges inside this yellow section, the strip. Now we care about this. This one is speed, this one is a field. So making the cross section, the cross multiplication, the cross product, we have this one. And then we can find the total EMF by moving the yellow part here from the first end to the second end, meaning that we have to take the integration with respect to rho from 0 to n. And there you are, EMF. This is the extended exercise of the previous one. We add another red bar opposite to the blue bar. I mean green bar. Okay. According to the exercise number 4, this one is the induced voltage at one end of the green bar. Similarly, we have the induced voltage at the other end of the red bar. And so the total potential difference between the two ends here and here will be this one minus this, which is 0. Okay. Please notice that in this case, because we don't have a closed path, so there is no current, but there are still induced voltage, because in this case we have an open circuit, for example. And now, using the second method here, we can redo the exercise number 1. Okay, instead of finding EMF basing on the magnetic flux, now we can use the motional EFI. This is a closed integral alongside 4 edges of this rectangular frame, so we can break up this one down into 4 sections. A to B, B to C, C to D, and D to A, like this. When I go from from D to A, it is exactly the exercise number 4. Okay, remember this. When a bar spins about its middle point inside a uniform field, so the total EMF between the two ends of the bar is 0. Okay. So according to the exercise number 5, the induced voltage between two ends of this edge is 0, because AD and BC, they are two bars rotating about their middle point, the center point. Now I can focus on this edge, for example, from A to B. From A to B here, the first term here is speed. The speed of any point on this edge will be the radius, which is r, multiplied to the angular frequency, which is omega. And the duration of this rotation is tangential, so its unit vector is a phi. Okay. And B here is a BAH. Computing this and taking the integration, we have this one. Please notice that this one is the integration with respect to space. But this one is a time. Time is a constant with respect to space, so we can put this one to the exterior of this integration. And finally, the integration of dz from L to minus L will be 2L. And there you are. Okay. Similarly, you can compute the induced voltage across the remaining edge from C to D. And totally, we found this. And this result here is exactly identical to what we found a long time ago. Bs omega sine of omega t. Okay. Next one is Bs omega sine of omega t. You can see that in this case, the second method is much longer and much more difficult than the first one. Are you all right? Okay, keep going. So far we didn't with. So far we worked on uniform fields. In this exercise, for the first time, we work with the time varying fields. The field here you see is spinning fields. If a rate of change is assigned, it depends on time. Okay. So now there are two ways to compute the EMF. The first one is to use the total magnetic flux. Okay. All right, total magnetic flux flow into this frame can be found from this. This one is B and this one is a ds. So you can see that it is rotating about this axis, z-axis. So this one is actually the direction of a row, because S here is the direction of any radius of this coordinate system. So actually AS here is a row, and the a row dot a row is 1. Then we have this. This one is a space integration, okay, the Poisson integration. So T here and T here, they are constant with respect to the space. And then we can change this one into this. The integration, the surface integration of ES is the total area of this rectangle, and is 2n times 2r. Okay, and here you can simplify this product into the sign of a double angle like this. This is the total magnetic flux, and to find the induced voltage, you can take the derivative plus 1 respect to time, and there you are. In this case, you can see that the angular frequency of the induced voltage is 2 times than that of the field or the frame. Are you okay? This is the first method. The second method is to use the motional EFI, meaning that we can rely on this formula. Okay, now I'm going to compute the two integrations here. For the first one will be the surface integration. Firstly, we can compute this derivative like this. Okay, and from this one, a row dot as will be 1. Like I told you, as is actually a row, and the derivative of sine will be cosine. Do not forget omega here. You have to multiply the result here to omega. Okay, do not forget this. And taking this integration, we finally come to this. So this is the first integration. The second integration is line integral. And like I showed you in the example number 5, we have to compute only the integration alongside the ABH, and we can double the results because the integration alongside this H and this S are all 0. Okay, taking this line integral, we came to this. We return to this. We found the first integration. We also found the second integral. Summing these two results, we, for the second time, came to the very results that we found 5 minutes ago. Okay, but once again, you can see that the second method is much more complicated and time-consuming than the first one. Because for the second method here, we have to compute 2 integrations. So if we have choices, we should choose the first method basing on the total magnetic flux. Okay. Are you all right? Any question? if there is no question, so I will talk about this. We are given a circular conducting loop, meaning a circle, okay, having a radius of r, and the system here is in the xy plane. The whole system is inside a field, and obviously this field is not uniform. This is a time varying field, and this field is the most complicated one so far. It has 3 components, and each component is assigned having different frequencies. You see, the first angular frequency is 500, the second one is 400, and the last one is a 314 radian per second. It's very complicated. Okay, now like usual, we have to find the induced voltage. I will use the first method basing on the magnetic flux. So firstly, I will compute the magnetic flux. This one is B. For ds here, let's say that its magnitude is ds and its unit vector is az. Do you understand this? Because the circular, the frame here is on the xy plane, so the vector being perpendicular to the xy plane is the z-axis, which is az. Now we can find the dot products. Ah dot az is 0, ay dot az is 0, and az dot az is 1. Okay, then here you are. We are only the last term here. Once again, t is a constant with respect to space, so we can move this one to the exterior of the integration. The integration here is now is the total area of the circle. And everybody knows that the area of a circle will be pi r squared, like this. And then, now finding the EMF is very simple. You take the derivative of this one with respect to time, and there you are. Are you okay? Please notice that EMF is potential, and potential doesn't have direction. So the final result here never has a unit vector. Never has a unit vector. Okay. Okay. I want you to do this mechanical exercise. I did this using the first method. I mean using the magnetic flux. Now I want you to apply the second method to find this EMF. Okay. All right. Go ahead. 10 minutes. You understand my requirement? I want you to apply this formula to find EMF of this exercise. Okay, this one will be much harder than the one that you saw on the screen, but if you can do that, if you can work it out, you will be very good at this kind of exercise. Okay guys, 10 minutes.
Teacher, you haven't turned on the mic.
Yes. Okay, it's time now to finish this morning. I want you to do the second, to do the last mid-class exercise. I change the direction of the loop. The loop here is perpendicular to the YZ plane and have an angle of 60 degree to the XY plane. And you have to redo this exercise by one of two methods, your choice. I recommend you to use the first method. Okay, go ahead, 5 more minutes. Okay, I repeat that. I change the direction of the loop. The loop here is perpendicular to the YZ plane and it creates an angle of 60 degrees to the XY plane. Please redo this exercise by one of two methods. All right, we stop here. Next week will be the last session of this course. Next week, I will finish this chapter, summarize the whole course, and answer your questions, if any. So be ready. Okay? Okay, that's all for today. See you next time. Goodbye, guys.
Goodbye, teacher.
Goodbye,
Bye-bye.
teacher.
Goodbye,
Bye-bye.
teacher.
Goodbye.